In this video, we will be talking about acid-base buffers. So we'll be describing where the buffer region is, why it is where it is, and what the purpose of buffers are, particularly in biological systems. A buffer is essentially a solution that contains both the acidic and basic form of a conjugate acid-base system where the two concentrations are in similar values. Buffers resist changes in pH, as we will see in some of the subsequent calculations that we will be working on. So we'll be looking at the pH change from the addition of both an acid and a base to a buffer system, and looking at how that compares to if we added that same strong acid and strong base to just pure water. The buffer range in an acid-base titration is where you have about a 10:1 to a 1:10 ratio of your acid to its conjugate base. So the lower limit of the buffering region is where you have 10 times as much of your acid and conjugate base in the acid form and only 1/10 as much in the base form. The upper region of the buffer area is where you have essentially 10 times as much of the conjugate base as you have the acid. So it works from a 10:1 to a 1:10 ratio of your acid to conjugate base. If we look at how that impacts in the Henderson-Hasselbalch equation, which there is a derivation in one of the previous videos, Henderson-Hasselbalch equation is pH is equal to the pKa plus the log of the ratio of the conjugate base to the acid. So if we plug in our values of 10:1 and 1:10, we will see that the pH in the lower region, the 10:1, the pH is equal to the pKa plus the log of 1/10, which is 1/10. So the log of 0.1 is -1. So the lower limit for the buffer region starts at a pH that is 1 less than the pKa value. If we go to the upper range of the buffer region, that's where it's a 1:10 ratio of acid to conjugate base. So its pH is equal to the pKa plus the log of essentially 10/1. 10/1 is 10. The log of 10 is 1. So the upper limit of your pH for the buffer region is 1 higher than your pKa. So this tells us that the buffer region in terms of pH starts at 1 unit below, 1 pH unit below the pKa, and ends at 1 unit above the pKa. One of the most common used acid-base buffers in biological systems is the carbonic acid, H2CO3, which is formed when carbon dioxide dissolves in water, reacts with the water to form carbonic acid. It can break apart or dissociate to give the acidic proton plus the bicarbonate ion, HCO3-, and this system has a pKa of 6.35. What this tells us is that the buffering range, where we can have a biological system use this as a buffer, the lower limit would be 1 pH unit less than this, so that would be 5.35, and the upper limit would be 7.35. The upper limit is where our body's pH works. It's in the low 7s for the pH, slightly basic solutions. Now let's look at some types of problems that we could do relating to buffers. And the purpose of these problems is to not only give us an idea of how to do the problems, but also to show why buffers are important. So we're going to start out by figuring out the pH of an initial buffer. So let's say we have a phosphate buffer, very commonly used in biological systems, that has 0.25 molar of H2PO4 and 0.125 molar of HPO4 2-. Now the way that you would get these in solutions is you would add some of the sodium phosphate monobasic and sodium phosphate dibasic into solutions, right? So commonly the way you get these is by adding salts of the acid and salts of the conjugate base. The most common one is sodium salts. Next we'll figure out what would happen to the pH if 5 mils of a fairly concentrated 1 molar hydrochloric acid solution were added to 100 mils of the buffer, and then compare that to water. We'll do the same thing for 5 mils of a 1 molar sodium hydroxide solution and look to see how the buffer handles that change compared to what it would be in regular water. So first part is to calculate the pH of the buffer that contains 2.50 molar H2PO4 and 0.125 molar HPO4 2-. Now there's two ways we can go about doing this. I'm going to show you first using an ice table, and then second we'll look at how to solve this using the Henderson-Hasselbalch equation. So our reaction would be, starting with the acid, H2PO4 minus. I'm going to use the shorthand form of H plus HPO4 2-. Now you could have adding water over here, and then this would be H3O plus, but more commonly you'll see it written in the shorthand notation. Filling out our ice table, initial, change, equilibrium. Our concentration here is 0.250. We're going to assume that the contribution from water is negligible, and then this would be 0.125. Now, because the concentration of H plus is virtually 0, what we're going to do is we're going to say that the reaction will shift to the right to make more H plus. So this will go down by X, H plus will go up by X, HPO4 2- will go up by X. So at equilibrium, this will be 0.250 minus X. This will be X, and this will be 0.125 plus X. Our Ka is products over reactants, leaving out pure liquids. So that's concentration of H plus times the concentration of HPO4 2- divided by H2PO4-. If we fill in our concentrations, our Ka would be equal to X times quantity 0.125 plus X divided by 0.250 minus X. Now, if we look at this, we're going to end up with a quadratic equation, which we can avoid the same way that we did when we were talking about equilibrium. Our Ka value, well, we have a pKa that's 7.21, which means the Ka for this process is about 10 to the negative 7.21. So it's a fairly small Ka value, meaning the reaction is not going to go very far to the right. And so we will try the assumption. We're going to assume that X is much less than 0.125. This will also fill in our assumption, or work for our assumption, that X is much less than 0.25. If X is much less than 0.125, then it's got to be much less than 0.25. So filling in our values, we get Ka is equal. So by doing the assumption, we're assuming that these X's are negligible. So we're going to get rid of them, which gives us Ka is equal to X times 0.125 divided by 0.250. Right? We're going to move everything but X to the other side, so we'll move this to the other side. So if we divide both sides by that, we get Ka times 0.250 over 0.125 is equal to X. So X will be essentially equal to our ratio here. If you plug it into the calculator, that's actually 2.00 to the correct number of significant figures. So this would Bx is equal to 2.00 times 10 to the negative 7.21. This value here is comes from our pKa, where Ka is equal to 10 raised to the negative of the pKa. So this value here will be equal to 1.2332 times 10 to the minus 7. This is equal to the concentration of our H plus, right? So if we want the pH is equal to the negative. Oh, before we go on, we should check our assumption. So we're going to check to see if this is less than 5% of this value. Just doing a quick look, this is much, much less than 5%, and so our assumption is good. Okay, so the pH is the negative log of our H plus. So if we take the negative log of our value here, right, plug it in, we get a pH that is 6.90897. In terms of significant figures, this value here had 3. You're taking 10 raised to an exponent. This one here had 2 values after the whole number on the exponent, and so that would mean that you have 2 decimal places for your scientific notation. So for our value here, we would have 2 decimal places in our scientific notation, so 3 significant figures. Taking the log of that value, we would have 3 sig figs there, so our number would be 6.91, right? It would be our pH going sort of the long way. We could also use the Henderson-Hasselbalch equation, which I'll do in blue. The Henderson-Hasselbalch equation says pH is equal, make this a little different blue, pH is equal to our pKa plus the log of our conjugate base A minus over HA, right? If we plug in our values, that means, so this little area here, we'll call that region for the Henderson-Hasselbalch. Our pH would be equal to 7.21 plus the log of 0.125 divided by 0.250, which is equal to 6.90897, which is the exact same answer that we got before, and to the correct number of significant figures, 6.91. Right? So the Henderson-Hasselbalch equation itself is actually a use or an interpretation of our ICE table. Right? So this is why when we were previously talking about the Henderson-Hasselbalch equation in a prior video, we said that it's really only good for a 1 to 10 to 10 to 1 ratio of our acid to conjugate base. And the reason why it's only really good over that, or really reliable over that region, is because that's where the region where our assumption, the assumption rule, this one right here, is going to be valid. Right? If you start going too far, or much outside of the range of a 1 to 10 and a 10 to 1, then one of your 2 concentrations is going to be very low, and so it will be comparable to the X value, making it not a valid assumption. We're now going to look at the effect of adding a strong acid to our buffer solution. what the strong acid is going to do is it will take the equivalent number of moles of the conjugate base and convert it back into the acid. So because it's the number of moles of the acid that we add that's converting the base back into the acidic form, we need to first know the number of moles of acid that we're adding. So we're adding 5 mils of a 1 molar solution. So that means that the number of moles of H plus that we're adding would be equal to 1.0 moles per liter times the volume that we're adding. So that's 0.0050 liters. Our liters cancel out. This will give us 0.0050 moles of H plus. And the reason we can call it H plus is because HCl is a strong acid, so it will completely disassociate into H plus and Cl minus ions. Okay, so this value here, right here, this is the number of moles of conjugate base that's going to be converted into acid. And so this is the number, or how many moles that our base will be going away and how many moles of conjugate acid will be increasing. So we first need to figure out how many moles of base we have. So that's moles of HPO4 2 minus. And then what we're going to do is we will subtract off the number of moles of that strong acid that we added. So the number of moles of our conjugate base would be, we first start with the concentration, 0.125 moles per liter times the volume. We're working with 100 mils of buffer, so that would be 0.1000 liters. So that gives us a 0.0125 moles. We're going to take this value and we're going to subtract our value from before. So we're going to subtract 0.0050 moles, giving us 0.0075 moles of HPO4. We're going to do the same thing for our acid. So that would be number of moles of H2PO4 minus, which will be 0.250 moles per liter times 100 mils, or 0.1000 liters. Liters cancel out. Now we're also going to this time we're going to add the 0.0050 moles of H plus, because that tells us how many moles of the base got converted back to the acid. So this value here is how much more acid we now have of the H2PO4 acid from adding the 5 mils of the 1 molar hydrochloric acid. So this will be 3.0 times 10 to the minus 2 moles. Now there's two ways to go about doing it from this point. One, we could recalculate the concentrations of both of our solutions and plug that into the Henderson-Hasselbalch. Another way of going about it is realizing that both of our acid and our conjugate base are in the exact same solution, and so the ratio of the moles is going to be the same as the ratio of the concentration. But to just be consistent, I'm going to show you how to calculate out the concentration of our acid and the conjugate base. Now, when we were doing this addition, adding the acid into our previous solution, our volume increased. And so we have to take that into account when we're trying to figure out the new concentration for the acid and its conjugate base. Right? We not only neutralized some of the base, but we also diluted the entire solution. So our concentration of our base, HPO4 2 minus, is equal to the number of moles divided by the volume. So that would be 0.0075 moles divided by the 100 mils we started with, 1000, plus the 5 mils that we added, so 0.0050. This comes out to be 7.14287 times 10 to the minus 2 molar. Doing the same thing for our HPO4 minus. This would be 0.030 moles divided by the same thing, 0.1000 plus 0.0050. This comes out to be 2.84514 times 10 to the minus 1 molar. Okay, we can now use our Henderson-Hasselbalch equation to figure out the pH. pH is equal to our pKa plus the log of the base form, which would be the HPO4 2 minus concentration divided by the concentration of our H2PO4 minus. All right, so that would be the pKa plus this value on top, that value on the bottom. That comes out to be 6.60794. In terms of significant figures, that gives us a 6.61 pH. Okay, now, previously we had our pH of the solution to start out with that we had done just before. The pH was equal to 6.91. In the buffer solution, after adding it, we had a 6.61. That's with HCl. Now we need to look to see what effect this would have if we did this with pure water. So let's see if we can fit everything in this little space for pure water to take a look at everything. Okay, so first we would need to figure out how many moles of acid we added, which is, we already figured that one out up here. Okay, and then our concentration of H plus would be equal to that number of moles divided by our volume. So that would be equal to 0.0050 divided by our 0.1000 plus 0.0050 liters, giving us a concentration of 4.76199 times 10 to the minus 2 molar. Okay, pH is the negative log of that. So if we were to take 5 mils of 1 molar hydrochloric acid, put it into pure water, we would expect that the pH would be the negative log of this concentration for H plus, which is pH equal 1.32. Okay, so our buffer solution started out here at 6.91. When we added the acid, the pH changed by only 0.3 pH units. If we were to add that same amount of acid to just water, you'd have a fairly acidic solution, 1.32 pH unit solution. So you can see that the buffer prevented a large change in pH. Now we're going to do the same process for using the same buffer, but now adding a strong base. So we're going to be adding 5 mils of a 1 molar sodium hydroxide solution and seeing what the buffer does, or how the buffer counteracts large changes in pH. So we're going to use a very similar process to what we were doing before. This time, the acid is being converted into the conjugate base, right? Because we're adding a strong base into the solution, we're neutralizing the acid. So we again need to figure out how much of it is changing. So we're going to figure out the number of moles of our hydroxide, which would be equal. Sodium hydroxide is a strong base, so it's going to break apart completely. So we're going to use 1.0 moles per liter times 0.0050 liters. Right, that's how much we added. So the total number of hydroxide ions that we're in essence adding by putting in the sodium hydroxide is 0.0050 moles of OH minus. This is the amount here. This is the amount of acid that's going to get converted into our conjugate base. So we can first figure out the number of moles of base. PO42 minus. This would be equal to our 0.125 moles per liter times 0.1000 liters. This time we're going to add to the base 0.0050 moles. These liters cancel out. That will give us 0.0175 moles of HPO42 minus. Figuring out the number of moles of H2PO4 single minus, this would be equal to 0.250 moles per liter times our 0.1000 liters. Liters cancel out. Okay, because we're adding a base, we're going to be neutralizing the acid, so we're going to be taking some of the acid, converting it to the conjugate base, so the acid will be going away. So this will be 0.0050 moles. Right, so that will be equal to 2.0 times 10 to the minus 2 moles. All right, so we're going to take our shortcut. This time we're just going to use the number of moles because we would be dividing it by the same volume, and eventually in the Henderson-Hasselbalch we're going to be taking the ratio. We can actually just use our moles. Right? So using the Henderson-Hasselbalch, pH is equal to pKa plus the log of our concentration of HPO42 minus divided by our concentration of H2PO4 minus. Now what we're essentially doing here is our concentration is the number of moles, HPO42 minus, divided by the volume that we have, the total volume, dividing it by the number of moles of our acid, H2PO4 minus, also divided by the total volume. So because we're taking the ratio, right, of these two values, and the denominator on both of those is the same, it actually cancels out. So, well, this would be plus RP pKa to make it consistent with the previous equation, right? And this is log, right? So because we're taking the ratio, we can also just use the number of moles of each, and so we don't actually have to calculate the concentration. So this is a little shorthand way of doing it. So our pH would be equal to our pKa, which is 7.21 plus the log of 0.0175 divided by 0.020. That's going to give us 7.15 for our pH. Right? So we added a good amount of base, and the pH shifted. It was, again, pH of the buffer was 6.91. pH with the NaOH, right? The pH of the buffer with the NaOH is now 7.15. If we didn't have the buffer, we can figure out our concentration or our pH if we added just the hydroxide. So our hydroxide ion concentration would be equal to the number of moles of hydroxide. So that would be 0.0050 moles divided by our total volume, which would be 0.1000 plus 0.0050. This would give us 4.7619 times 10 to the minus 2 molar. We can find the pOH, which is the negative log of that value, negative log of our OH minus concentration. Take the negative log of this value here, you'll get 1.32, and then pH would be equal to our pKw minus our pOH. So the pH would be equal to 14 minus 1.32. So our pH of just water, if we added that same amount of base, would be 12.68. Right, so you can see the effect of a buffer. If we had just water and we added 5 mils of a 1 molar sodium hydroxide solution, the entire solution would become fairly basic at a pH of 12.68. But with the buffer solution, the pH only increased by about 2.5. So that's essentially the reason why we have buffers, is so that we can prevent large changes in pH.